I'd like to look at problem 34. In this problem, they give us a function f that's 0 everywhere in the interval 0, 1, except at x equals 0, where it takes height 1. So let's make our little grid here, and we'll put a height of 1 at x equals 0, and so we'll put an open circle here and kind of shade in the rest, because that function's value is 0 everywhere else in the interval 0, 1 except at 1. And so we'll kind of take 0, 1 to be the domain of this function, the interval 0, 1, and that's it. So our job here is to show if p is a partition of 0, 1, then 0 is less than the up of f. Now up of f is referring to the upper Riemann sum with respect to a partition, because that p is in there. So we have to create a partition, and then we have to compute this upper Riemann sum using this definition. Now it comes down to these yi's, and when we make our partition, so let's let p equal t0, t1, and so on, all the way to tn. So let that be a partition of the interval 0, 1. Now what that means is, so i.e., it means that the t0 that we pick is the left endpoint. It's 0. Then it means that t0 is less than t1 is less than so on and less than tn, and tn is 1. It means it's the right endpoint. So we have so many points in between, and we have a left one and a right one, and that's it. So in the middle here we'll have some kind of t1, then we'll have a t2, and so on, and then we'll finally end at tn. And that's our partition. Now it's important to remember that t0 is 0. So t1 is strictly bigger than 0. That's part of the definition of a partition. Now when I compute the integral, the upper Riemann integral, Riemann sum, my apologies, upper Riemann sum, I need to compute these yi numbers. And by the definition of the yi numbers, if I took I equal 1, because that's the smallest value of I I'm allowed to take according to the definition, I'll have the interval from t0 to t1. So that's referring to, from my starting value on the bottom to my first red tick mark, wherever it may be. Because we're not making an argument about a specific partition, we're trying to argue about any partition here. So I'm looking on that interval, and it's telling me to take the least upper bound of the value of f of x, for any x in there. Well, there's only two values that f of x can take for x's in here. It's this height at 1, which occurs at the left endpoint of that interval, and then there's 0, and that's the only one. So, you're looking for the least upper bound of, the point set 0, 1. If you have a maximum in a point set, the least upper bound is the maximum. That's, it's the rightmost point, so to speak. So this is our y1 is 0. Now if we were computing a lower Riemann sum, we would be taking the greatest lower bound of this set, and a greatest lower bound is like a leftmost point, so it would be telling us the a value of 0, but it doesn't. Now on this next interval, we're focusing all of our attention in here. I shouldn't really draw a rectangle there. But we're focusing all of our attention now on this subinterval, with starting at the first tick mark going to the next one, and we want to find the least upper bound of values of f of x restricted to that interval. Well, f of x is identically 0 on that interval. It never deviates from 0. So you would say that y2 is 0. And so on. Okay, and since this function is 0 everywhere, you'll have up to yn being 0. So we have all these y's. They're all 0 except y1, which is 0. Now we could have many, many more partition points in here. As many as you want. As long as you have a finite number, it's fine. And they're ordered correctly. So now I want to compute the upper Riemann sum over that partition P that I've specified here of the function f. And by definition, that comes to this sum. This is the area of rectangles. And the point of these y's is they tell you the height of the rectangles. So the first rectangle is at height 1, and it has width, t1 in this case. And so that's what ti minus 1 will become. So this is the sum, by the definition, of yi ti minus ti minus 1. That's your sum. Now, if I is 1, I get y1 t1 minus t0 plus, and then I'll have y2 and y3 and so on, but those are all 0, so I'm just going to write 0 there. Okay, because 0 times anything is 0. And this is not function evaluation, this is multiplication. Now y1 was 1. t1, we don't know what t1 is. Could be anything. Well, anything in the interval 0, 1, except for 0 and except for 1, some positive number. But we do know t0 is 0. So this value is t1. But t1, by definition of a partition, is positive. I mean, reading this right to left, it says that t1 is greater than 0. And that concludes, number 1, right? It says, problem number 1 in problem 34 says just show that this, upper Riemann sum over any partition is positive, and we just did that. Now, look at number 2. If epsilon is greater than 0, then there's a partition P of 0, 1, such that UPF is less than epsilon. Well, if you give me an epsilon, so if I have this epsilon in my hand, so we start with it, then I can use it for stuff. And my job here is to find a partition such that UPF is less than epsilon. Well, if I think of my construction here, every partition point other than T1 was worthless, right? And I have an exact formula for my upper Riemann sum in terms of my partition. And the only thing that matters is T1. Now, I'm going to have to make a partition, and part of the definition of a partition is that you have a left endpoint as the first value, and you have the right endpoint as the last value. And I'm only going to take 3 points in my partition. I only need those because the definition requires me to have a first point and an end point, and this one I have freedom over. Now, for this particular problem, they're asking me to produce a partition. It says there is a partition, so I have to make one. And I'm going to make the partition in terms of my number epsilon. So I'm going to make T1, let's say epsilon over 2. Now, therefore, UP of F from earlier is equal to, it's equal to T1, which by my choice of my partition, I chose to be epsilon over 2. Now, if I divide something in half that's positive, I certainly get something smaller. And that does it, right? So I can make upper partitions, or upper Riemann sums, arbitrarily small by picking certain partitions. Finally, for question 3. Question 3 is very similar to question 1. Maybe I can even fit it on the same page. Question 3 asked me to show that 0 is the only lower Riemann sum for F. And so what that means is that I'm able to always get the same Riemann sum for every partition. Now, for the definition of lower Riemann sum, so just like on the previous example, I was able to always compute, the upper integral, but it was always a different value. So now they're telling me in number 3, maybe I'll do it in red, in number 3, I should only get 0 as the lower Riemann sum, no other option. So let's look at the partition we've already drawn. We have this partition, and we have our subintervals. If I now pick the correct y's for lower Riemann sum, and in that case I choose the greatest lower bound, then I'm always picking the smallest value that f takes on this interval. I think this yellow worked pretty well last time. So I'll get, can you see that? Yeah, you can, good enough. If y1 for a lower Riemann sum is 0, and all these are also 0. So what that means is, because I'm picking lowest bounds, I'm always picking the minimums if there is a minimum, or I pick the smallest, first point to the left. But no matter what t1 I pick, I still have a gap between 0 and that t1. Therefore, I'm always going to pick the height of 0 there, and that's all I need. So for number 3, I can now compute LPF, and it's the same formula that we had before. It's the sum from I equal 1 to n, but this case I'm picking the yellow yi's times ti minus 1, and these are all equal to 0. So I end up with 0 plus 0 plus 0, and that's of course 0. And that concludes that proof.